Hi, and welcome to another math video. I hope you're having a wonderful, well, I'm recording this Friday night, but I think I won't put it up till tomorrow because it's Friday night. I got places to be. So I'm going to try to make this quick, though it might be about an hour. Okay, so, okay, what are we going to do? In the last video, we talked about the discrete Fourier uncertainty principle and just examples of that. And then at the very, very end, we stated the theorem. And so now we're just going to go jump right in and prove the theorem. But first, we're going to prove a ton of little lemmas. And these are lemmas that you have probably seen before if you have done anything with Fourier, any kind of like Fourier analysis on groups. But I'm going to state and prove them here. And so I'll put little timestamps if you just want to go to the proof. Okay, I'll tell you the lemmas. One is the orthogonality of characters, then Parseval's identity, then the Fourier inversion formula, and then the Cauchy Schwarz inequality for real numbers, which these are all things that you may have seen before, so you could skip all of them and go straight to proof if you want. If not, then buckle up. Okay, so I'll try to write properly. Oh, you know what? I'm gonna make this. Sorry, just a little OCD there. Okay, so the first lemma, as I said, we're going to show that characters are orthogonal. So all of these were defined in the previous video. So for any characters, chi1, chi2 in the group of characters on Z. So these are homomorphisms from Z to the complex numbers. We have the inner product, chi1, chi2, which of course is this expectation in Z of chi1x, chi2x, complex conjugate. This is equal to 1 if chi1, that's a funny chi, equals chi2, and 0 otherwise. Okay, so that means it's orthogonal. So, if you think of orthogonality of vectors, you find the dot product between two vectors, which is their inner product in that space. And then if it's 0, they're orthogonal. So this shows that it's actually an orthonormal. Okay, so we're skipping a little bit, but we actually show that the characters form an orthonormal basis of the whole space of functions from Z to complex numbers. Okay, and likewise, if these aren't characters, but if x and y are in Z, okay, we have this sum over chi in Z hat of chi of x, chi of y bar, and this is equal to, well, it's not an average this time, it's an actual, bona fide sum. So we have the size of Z hat if x equals y and 0 otherwise. Okay, and so we'll talk about what this means later. Let's just prove it for now. So this is a pretty standard proof. So first, let chi naught denote the trivial character. We have this. Okay, so if we sum, we take the average over all of Z of chi naught of x, okay, well, that's just the expectation of this constant function 1, which is 1, okay? On the other hand, if chi is non-trivial, then there is some u in Z such that u is not equal to 1, right? Now, just because we assume that chi is non-trivial. So we take the same sum, expectation of chi in Z, x in Z of chi of x, but this is the same as the expectation. Summing over all x and z is the same as summing over all u plus x and z, because z is a finite group, or it doesn't even have to be finite, but you know what I mean. So x in z, u plus x. Okay, so we're just like rearranging the sum, really. Okay, but because chi is a homomorphism, okay, this gives us expectation times x and z, chi of u, chi of x. Okay, but then since this is not, we can do this no matter what. We can just take this out of the sum, right? So chi of u, expectation of x and z, chi of x. Okay, but what have we done? So we've shown that this is not 1, but somehow this expectation and this expectation are the same on both sides, and this isn't 1. So what do we have to conclude? We have to conclude that expectation of x and z, chi of x, is equal to 0. Okay, so any non-trivial character, if you sum over the whole group, you get 0. Okay, so what does that mean for our inner product? Well, consider chi equals chi 1, chi 2 bar. Okay, then if chi 1 equals chi 2, this is chi 0. Okay, because, well, you can, it's the, everything's around the unit circle, right? So if you take chi and then you conjugate it, everything chi, you conjugate it, it's actually the, is that correct? Yeah, it's the inverse. So everything will be trivial, will become 1. Okay, so this is chi 0, and we have chi 1, chi 2, the inner product equals 1 by the first case. Okay, sorry, my writing's really bad. And if not, then, well, yeah, okay, I don't even know why I'm writing all this. Chi 1, chi 2 is equal to this thing, right? So x in z chi x, for some non-trivial character chi, which we showed has to be 0. Okay? Now, the proof for the next, for the other statement is like literally the same, but I'll just do it anyway. Okay? I mean, it's not literally the same, but it's like the dual of the same thing. Wait, where did I put that? On a different page. So let's just say, we'll go through really fast. So chi x, chi of y is equal to chi of x minus y, right? So if x minus y is equal to 0, i.e. if x equals y, then sum of chi in z, chi in z of the sum over all chi of chi x minus y. So overall chi of chi x minus y is equal to, well, if x minus y is 0, this is going to be 1, 1, 1, 1, 1. So it's the size of z hat. Sorry, this is z hat. Okay, and if not, if x minus y, if x is not y, then there must be some homomorphism psi such that psi of x minus y is not equal to 1. Okay, this is because, well, if there isn't, then x minus y has to be 0. Okay. Just think about it. So chi in z, so the chi in z hat, take the same sum, x minus y, and now we do the same thing, we factor it out. The summing over all chi is the same as summing over all psi x minus y, like some fixed psi, and then chi x minus y. Make sense? So, I mean, we're taking the group element psi times chi, okay? Okay, and then, so this is the same as chi in z hat. Oh, sorry, whatever. We have to take it outside the sum, right? Psi x minus y, chi in z hat, chi x minus y. And now we see that this is 0, okay? And then we do the same thing. Well, I forgot a bar here, but that's the inside of that inner product. Okay? So we're done. Not dwell too much on that. What we will dwell on is what this means. So, let me just take my notes. Okay, so remember in the previous video, we showed that you can get so for each x in z, we get a character by taking, so z, this is the product of cyclic groups, say. Okay, we got a character for each x by setting chi x, sorry, let's make this a u, so that x can be the, sorry, let's do, oh my god, okay, is there an eraser? The technology is difficult, NR, okay, by setting chi u to be the function of x that equals e to the 2 pi I ui xi over ni, where obviously u is some tuple. You can regard u as some tuple of r elements of these cyclic groups, and so x is also some tuple, and okay, so that's a character. But we can also, so this is a chi u goes from z to the complex numbers, but we can also get a function from the dual group back to the complex numbers. So we could just do this. So fx of chi is equal to chi of x. Okay, so now now fx is equal to, goes from, takes elements of, the dual takes homomorphisms and evaluates them to get some complex number. So what we've shown is, that this set chi u for u in z and this other set fx for x in z, z, not z hat, okay, are orthogonal bases for, well, they're orthogonal sets, and they're bases because, just give me a second, for c to the z and c to the z hat, respectively. Okay, so we showed that they're orthogonal. In fact, the first one is orthonormal. And they must be a basis because you have n, so this is a space of dimension n, right? They're functions from z to c. It's pretty clear that, there's only z, degrees of freedom, so it's a space of dimension z. And we have found dimension size of z, which is, say, n, and we just found n orthogonal vectors in that space. And same for the second one. Okay? So this is going to come in a little bit later. Actually, yeah, it shows up. I don't know where it shows up. I do know it shows up way later on. I don't know if it shows up today again, but it's good to know. All right, so next, lemma. Parseval's identity. This is super useful. So whenever I see Parseval's identity, I think of Albus Dumbledore. I think that's one of his middle names. Something like that. Okay, so let Z be a finite Abelian group. Don't you wish all groups were Abelian? Okay. And let F and g go from z to fixed numbers. Now, let f hat and g hat be the Fourier transforms. Actually, let's write it. Let f hat, g hat be the Fourier transforms. If you forget what a Fourier transform is, you can look at the previous video of f and g. And, okay, then what Parseval's identity says is then the inner product of f and g in the one space is equal to the inner product of f hat, g hat. Now remember, the definitions of inner product are slightly different. One of them is an expectation, and one of them is a actual sum, right? And, you know, so we kind of do, there's a little bit of hacking here to make sure to actually make these equal, but everything works out fine. So let's get to the proof of this. We'll need a new page. So, okay, well, I think I can scroll up. So, okay, yeah. It's not what we're trying to prove. We're trying to prove that the inner product of f and g is the same as the inner product of the Fourier transforms of f and g, respectively. Okay, let's go on the whole new page. Proof. Okay, so let's expand all the definitions. Expanding all the definitions. And then rearrange sums. And rearranging sums, we get, okay, so we start with f hat g hat. Okay, it's slightly easier, which is the sum overall chi in z hat, f hat chi, g hat chi bar, right? Okay, now let's expand this whole thing out. So of course the sum stays the same, but f hat of chi is this expectation of x in z, f of x, chi of x bar. And then g hat is the same thing. Let's use a different variable in z, g of y, chi of y bar. But this whole thing is bar, okay? Now, what do you do when you see a bunch of sums? You should, let's just take the sum in a different order. Again, we can do this because it's all finite, so we're just rearranging. Expectation of x in z, f of x. So we pull out the f of x, and then let's pull out the y in z, g of y. Okay, let's figure out this is bar. So this is barred once, right? So that's bar. And then everything else, depending on chi, goes on the inside. So chi lambda in z hat, chi of x. So chi of x is, did I get the bars all wrong? I hope not. Okay, so chi of x is not barred. Okay, let's just see if the bars are wrong. So I think chi of x here is not barred, right? So, sorry, is barred. And chi of y is not barred, because it was barred twice. Okay, so by the second part of the previous lemma, you'll note part of the previous lemma. This part in here looks like what we showed above. It has to be 0, right? Or it's not 0. It's 0 whenever x and y are different, and it is equal to the size of z hat when x equals y. Okay, let's write that. So expectation of sum of all chi in z hat of chi of x, chi of y, and I think chi of x is barred. My notes I think are wrong. I'm trying to do it correctly up here. This is equal to 0 to z if x equals y and 0 otherwise. Okay, so what that means is this whole thing in here, so this thing, the only term that survives is where, Sorry, let me look at this. No, I should not look at it this way. Because we fixed x like right at the beginning, the only term in here that survives, okay, is where these are y is equal to x. And when y is equal to x, this thing is the size of z. So this expectation over the size of z, over all z is like kind of canceled out. And then the only thing here is g of x because y equals x. Okay, so what am I trying to say? So for any fixed x, expectation of y in overall y in z, g of y bar, sum chi in z hat, chi of x, chi of y, that's equal to g of x bar. Okay? And that's why the bars, like, so even though I got the bars wrong, it doesn't matter, because that kind of just cancels out. And hence, f hat g hat inner product is equal to expectation of x in z, f of x, g of x bar, right? Well, that's just f g inner product. It is kind of nifty. We want. Okay, so that's Parseval's identity, and okay, so the computation we did here is actually the exact same computation in the next. So in a way, we might have been able to do the proofs in the other order, but no matter. Let's do it this way. So lemma 3, Fourier inversion formula. So f it goes from z to complex numbers. We have, and then f hat is its Fourier transform. We have f of x is equal to sum overall chi in z hat, f hat of chi of x. Okay, and because remember we showed earlier that the characters are an orthonormal basis for the space of all functions from z to c, this gives us the coefficients. So kind of the coefficients in that linear combination, like expressing x, f as a linear combination of these characters, the coefficients are exactly the Fourier coefficients. Okay, that's what this is saying. And again, so the proof, expand, so we expand the this thing, expand the definition of Fourier transform. Okay, all kinds of hat. That's the expectation of y in z. F of y, chi of y bar, and there's a remaining chi, right? But then if we pull, we pull all the things that don't depend on chi out, y and z, f of y, and then everything inside of here, chi in z hat. That writing is so difficult. Okay, everything that's in here, so it's chi of x, chi of y. Okay, and we just showed that literally just in the previous lemma, we literally showed that this thing is just equal to whatever's here of x, right? So this is f of x. Over there we had g bar of x, right? So we had g bar of y, and we showed this whole thing became g bar of x. But here it's equal to f of x. Okay. So we actually proved the Fourier inversion formula halfway through the Parseval's identity, the proof of Parseval's identity. So we could have actually proved Fourier inversion first, and then not had to do the same thing twice. But that is okay. We do not need to do things perfectly. We are but human. All right. Next, next I'm going to prove Cauchy Schwarz, the Cauchy Schwarz inequality for real numbers, and there's like literally no reason to do this, but it's for completion's sake. Also, I'll just show you a cool proof that I don't think this is like how it was proved in my analysis class, but it's how it was proved by like my master's supervisor. in a comp sci class, and it's like pretty famous. And this only works in R. Okay, so it's the real version, but it's all we'll need because we're going to be using it with norms of things, and norms of complex numbers are real. So let u1 up to un and v1 up to vn be real numbers. Okay, so you can think of them as vectors. You can think of them as just like two lists of real numbers. Okay, then this is the Cauchy Schwarz inequality. I equals 1 to n ui vi squared is less than equal to the norm of this vector, I equals 1 to n ui squared, and times the norm of this vector, I equals 1 to n vi squared. Okay? And I'll give a little nifty proof that, yeah, it's the one that I saw. So you consider this polynomial in x, okay? It's equal to the sum of I equals 1 to n ui x minus vi squared, okay? And if you expand all this out, okay, you expand not all of it, you just expand this binomial out, you get, so the coefficient of x squared is this ui squared, okay, and then you minus 2x I equals 1 to n ui vi, and then the constant term is the vi squareds, right? So I equals 1 to n vi squared. Okay, but so this polynomial is a sum of non-negative things. So each of these, I mean, it could be positive or negative, it's a difference, but then you square it, so it's non-negative, and you're summing n non-negative things up. Since p of x is non-negative, okay, this polynomial has discriminant, I don't know if that, discriminant, not bad, non-positive, has non-positive discriminant. And what's the discriminant? That's the, if ax squared plus bx plus c, the discriminant is in the quadratic formula, it's the thing underneath the square root, b squared minus 4ac, which you know from kindergarten. So what exactly is a here? So a is equal to the sum of I equals 1 to n ui squared. B is equal to minus 2 ui vi equals 1 to n. And C is equal to I equals 1 to n vi squared. And now, literally, you just need to do this. The observation is that this is non-positive. So if this thing is non-positive, so it's less than or equal to 0, then we have b squared is less than or equal to 4ac. Okay, so what's b squared? That's 4 times sum I equals 1 to n ui vi squared. And what's 4 times ac? 4a ui squared, and c is vi squared. Okay, I'm not going to write the indices. And you have the Cauchy Schwarz inequality. I thought this was a really cool proof. Okay, so even though you've no doubt seen the Cauchy Schwarz inequality before, maybe you haven't seen the proof. All right, so now this is the end of like generic things. Now we're going to prove a lemma that's like directly related to, it's still a pretty simple lemma, but it's at least like we're getting closer to the theorem. So we should define something. So if f goes from A to some group, A is a finite group, A to the complex numbers, A is a finite group, we can write the norm of, the infinity norm is just the max overall x in A. X in A. Okay, so this is the L infinity norm. So what does this lemma say? So let f go from Z to C, then the infinity norm of the Fourier transform is less than or equal to the expectation for all x and z of f of x, absolute value. Okay? And it's not super difficult. Actually, I don't even know why I made this as a separate one. Yeah, like we could have just done it directly in the theorem. Okay, but it's fine. So let proof. Let chi in z hat be given. Okay, so because this is a max right here, so that's why we'll just let a chi be given. To apply f hat on. Then with this chi, we will have f hat of chi is equal to, right? F hat is, it's just taking the inner product of f with chi, so expectation of x in z, f of x, chi of x bar. Okay, and that's less than or equal to, this is the triangle inequality. You just, the absolute value of a sum is less than the sum of the absolute values. So expectation of x in z, f of x, chi of x bar. Okay, but remember, we way back, we observed that because x is a finite, or z is a finite group, z is a finite group, and chi is a homomorphism from z to c, some power of chi of x is going to have to be 1, which means that chi of x has to have norm 1. Okay, so since this has norm 1, we can just get rid of it. Woohoo. And that's exactly what we're trying to prove, right? So we are done. And we're done because chi was arbitrary. This works for all chi, so if this works for all chi, finally many times, then it works for the max. Okay. Now we are ready to state. I'll state the Fourier uncertainty principle again because no doubt you have forgotten it. I can't even remember what I did like 3 days ago. So let's make a new page. All right, Fourier uncertainty. We are theorem Fourier uncertainty principle. Okay, so let f be a function from z to c, z's finite group, and let it be non-trivial. And by non-trivial, we mean it's not identically 0, identically 1. Okay, so then we have, do we mean identically 0 or identically 1? I think we mean 0, sorry. Okay, we have, remember we use this, 0th norm is the size of the support. The size of the support of f times the size of the support of f hat is greater than or equal to z. We spent a very long time doing examples last time. I hope you enjoyed that. More likely you didn't enjoy it. It was very tedious. By the previous lemma, okay, and the definition, wow, of support. Okay, what we're going to do, it's kind of a tricksy thing where you're going to do everything in terms of this max. Okay, so we have this bound that we did in the previous lemma, the L infinity norm of f hat is less than or equal to expectation of x in z, f of x, and of course this is 1 over the size of z, expectation of x, or sum over x in z, f of x. Okay, and the definitions of support, well, f is 0 outside of the support, so this is the same as taking the sum over x in support of f. Okay, f of x. Okay, now we use the Cauchy Schwarz inequality. Now note that f of x is a complex number, but you take the norm, so it's real numbers. And by the Cauchy Schwarz inequality, we can show this. So sum over, so by Cauchy Schwarz, sum over x in support of f, f of x, if there's no squared, right? Yeah. Let's be extra explicit. Times 1, okay, is less than equal to. Remember, there's a squared before, so now we have to put a square root. Sum over x in support of f of x squared, and then this thing, x in support of f 1 squared. But this is just the size of the support of f, right? So that's equal to big square root. That's the size of the support of f. So f, the 0 norm of f, kind of, and then the rest is the same. Okay, so things are starting to pop out, right? So far, actually, let's just say what we've done so far. So far we've shown that f hat infinity norm is less than or equal to 1 over z times this thing. So 1 over z times this thing. F of x squared. Okay. Now, by Parseval's, now we use Parseval's inequality. So and we don't need to put the support of f here anymore. Let's just put z. Okay, it's the same thing. We don't care. So there's s just z here. By Parseval's identity. Okay. This thing, well, the reason we take it over all z again is because in Parseval's identity we need the whole of z. So f of x squared, this is equal to, so the norm of f of x is the same as the f of x times f of x bar, right? That's how complex numbers work. So, yeah, so this is the inner product between f and f. Okay, but that's the same as the inner product between f hat and f hat. And if we expand that out, it's chi in z hat, f hat of chi, f hat of chi bar, but we just said that that's the same thing as the norm squared. Okay, and this, okay, let's just think about this. We take a we can take it as just less than z times, so z hat has the same size as z. Then we upper bound f hat, like kind of universally upper bound f hat of chi, and we can do that, or sorry, f hat of chi squared. We can do that by taking f hat, like how many elements there are, and then the max of how big an element can be. Does that make sense? So this squared, if you think about this squared, right, it should be counting, you know, like n squared things. N is the size of the group. It should be counting n squared things. Okay, so and that's in the square already, and then it goes over n again. So there's n, then there's some sum of n squared things, but so first we take the size of the support, so that takes out all the 0 things, and then we just upper bound it by the biggest f could possibly be. Okay, so I'm gonna have to stare at that a little bit, but it's not so hard. And then now let's plug this in. So this thing is that we plug it in up here, and give us so f hat, I wish I could see everything at once. That'd be really nice. F hat of infinity, L infinity of f hat, sorry, is less than or equal to 1 over z. Okay, now, sorry, was there a squared here? Yes, there's a squared. Well, there's a squared. Okay. Yeah, so this is the size of support. This is how big the thing could actually be. I hope that's right. Okay. Now, 1 over z square root f. Okay, now we have z, we have an f hat, and we have an f hat square. The L infinity. Okay, now this is equal to the z. This is an actual z in the denominator, and there's a square root on top. So there's a square root of z at the bottom. And then there's a square root of f hat, or sorry, f and f hat. And then here we have the infinity norm, and we have the infinity norm again. It's squared here, so it comes out of the square root. And because, sorry, this is f hat. And because f is, we assume f to be non-zero, that means that it has, its maximum is not zero, and also its f hat, its maximum is not zero. So, so we can divide, and so we get 1. You can rearrange, right? So 1 equals 1 f hat z, and this is the same thing as saying that z, oh sorry, this is less than equal to, z is less than equal to f hat. Okay, and we are done. And you know what, I'm just going to because it's bothering me a little bit, you can tune out, this is the end of the video. But it is bothering me a little bit what happened up here. There was a squared that when I was like staring at it, I was convinced it was correct without that squared. Okay. Z, support of f hat. I don't have minutes. So the support of f hat, chi and z hat, support the f is the biggest it could possibly be. Yeah, it seems like there should be, this thing shouldn't be here. Am I going crazy? I don't know, like, this is the biggest that f hat of chi squared could possibly be. It's a square, but the square's on the outside. Squared. Okay, give me a sec. I'm gonna pull up my notes. This is, I'm sure, like completely riveting programming. But let's just, I'm stupid. Okay, so what happened is I forgot. This thing, okay, first of all, this thing is not that, right? Because this is a sum, so there's an expectation here. So this is size of z. There we go. Oh, there we go. There's z here. and the z's here. Okay, wonderful. It's a good thing that we did it, because otherwise I was pulling the wool over your eyes. But we figured it out. Everything's correct. Good thing you stuck around and didn't just like tune out, because then you would have the wrong thing. Okay, that was a little bit embarrassing towards the end, but we did it. We proved the uncertainty principle. So just foreshadow what's going to happen next. I think I will continue this series of lectures. It's like 2 videos we were able to prove this uncertainty principle. But there's another uncertainty principle that when we showed that this holds, right? F, size of support of F, size of support of F hat is greater than or equal to Z. Okay, but when Z equals ZP, a cyclic group of prime order, we can actually show that something better. We can show F, the support of F, size of support of F, plus the size of the support of F hat is greater than or equal to P plus 1, which is the size of Z plus 1. And this is obviously a much better bound, right? Because it's saying that something like, what does this bound say additively, right? We're saying that, well, they could be something like square root of n, so if Z is n, they could both be something like square root of n, right, times 2. But this is showing something a lot bigger. They're actually a lot bigger than that. And remember, in our example way back when, for Z3 and Z5, we got like 3 times 1 and then 5 times 1. So yeah, for Z5, there's like, this is 1 and this is 5. Okay, so it's actually meeting both bounds, because 5 times 1 is 5, but 5 plus 1 is 5 plus 1. Sometimes I say the weirdest things, but you know what I was trying to mean there. Okay. That is what we are going to prove for the remainder of this series, but it's going to take us on a very long journey. Like, we are going to have to learn about cyclotomic polynomials. We're going to have to learn about these van der Monde matrices. And then I think we're ready to do the proof. But it'll be like at least like 4 more videos, maybe like 6 more videos. Okay? And they're going to come up slowly, so you can be excited for that. It's a cool, I think it's a cool result, but just the math that we'll have to go through to prove it is also, I think, it's about the journey. Mindless Cyrus is about that. Okay. Well, until next time, go and have fun in life.